Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 7. Finite Volume Method for Ordinary Differential Equations. Example. Let us consider the following two-point linear boundary value problem in conservative form. We will obtain the numerical solution using the finite volume method with m equals 5 and 10 uniform cells, and compare the estimates with the given true solution. To obtain estimates using the finite volume method, we will follow the steps below. Gridding, discretizing, implementing boundary conditions, constructing a linear system of equations, solving the linear system. We will carry out the numerical procedure for the generalized case. The solution domain is divided into m cells, and physical nodes are placed at the endpoints of each cell, as illustrated. The control volume boundaries for the ith cell are marked, and the abscisses for uniform cells are determined as follows. The governing ordinary differential equation is integrated over a control volume x from xi minus 1 over 2 to xi plus 1 over 2. Integrating over the ith cell over this interval yields the integral term on the right-hand side yields. Note that this integration was carried out exactly, not approximately, so we can expect better solutions. Since the function p, which is equal to x plus 1, is continuous throughout the solution domain, hence, the first integral term can be expressed as follows. To approximate the integral, we will replace the first derivatives with the central difference formulas. This approximation, which is second-order accurate, becomes the second integral term on the left-hand side yields. Collecting the approximations for the three integrals for an interior cell, we obtain the general discretized equation, where bi, di, ai, and ci are defined as follows. Implementing the Dirichlet boundary condition to the right boundary node, labeled as I equals m, is done by setting dm equals 1, bm equals 0, cm equals 13. For the Newman boundary condition on the left boundary node, we integrate over a half cell, that is, x from 0 to h over 2. Integrating the first term gives the first derivative at x equals h over 2 is approximated with the central difference formula. The derivative at x equals 0 is the left boundary condition, which can be readily substituted. Integrating the second term gives the third integral term on the RHS becomes collecting all the terms, the difference equation for the left boundary node becomes. For left boundary node, we can express the difference equation as where the coefficients of the difference equation can be written as follows. The finite volume method discretized equations for interior nodes and those equations derived for the boundary nodes constitute a tridiagonal system of linear equations that can be expressed as a matrix equation, where the coefficient matrix A and the right-hand side vector C for m equals 5 cell case are found as follows. The solution of the tridiagonal system for 5 cells is tabulated along with the true solution as well as absolute true errors. The errors are in the order of 10 to the minus 2. Solving the boundary value problem with 10 cells results in numerical estimates with errors in the order of 10 to the minus 3. In fact, the true errors of the estimates with 10 cells are about a quarter of those made with m equals 5 cells. This is not surprising since the finite volume is a second-order method. Thus, the order of accuracy becomes h over 2 squared. With this note, we end this lecture. That is all for now. See you next time with another topic. Bye.